So, so far we have looked at categories. Then in a category, the objects are not really very important, right? Objects can always be replaced by the corresponding identity morphisms. So I'm saying that there is an injective mapping of objects into morphisms. Similarly, objects are not really important. Like in categories, functors are more natural objects to consider. So every object can be thought of as a functor in a precise way. Yeah, I mean, we are going to deal with something very specific, but I'm going to remind you of this first example on the screen right now. Yeah, look at this example, like vector spaces. A finite dimensional is not really important. Vector spaces to opposite of vector spaces. We were still talking about something. What is that dual functor? What is the dual functor? What does it do? It takes a vector space and then maps it to what? V star. But what is V star? Collection of all functionals, and functional is defined to be a V to R, right? So if I rewrite this slightly, or maybe it was written on a previous yes. So I'm just going to write it over here. This is home VR. So what if I say that home VR is nothing but home RVR? I'm going to rewrite it as home sub R blank R applied on V. Okay, so this R, tell me this, is R an object of this category? The category of R vector spaces? Yes. When I say home sub R, then I am taking all R linear maps from V to R. So that means implicitly I am assuming that V is a real vector space, R is a real vector space. So I am taking two different objects of the category. So I am looking at the home set. Right? So this home set is a very important object of study. So let me write something about it. So this is, so throughout this lecture, yeah, C is a locally small category. Locally small means the home sets are actually small sets, which means that home lands inside sets. It takes two arguments. Yeah, if I write home AB, then it takes two arguments, A and B, both are objects, but in one of the components, it is covariant, in another component, it is contravariant. Which component is it covariant? No, not the first one, the second one. See, when I said home blank R, then that was a map from R vec to R vect op. Yeah, it became a contravariant functor. Yeah, the blank in the first, like second, if you fix, then it becomes a contravariant functor. If you fix the first one, then it becomes a covariant functor. So what I'm saying that C A blank from, it's a functor from what to what? It's because it's a locally small category, it's a functor to the category of sets, and it's a functor from C to sets. And on the other hand, C blank B is a functor from C op to sets. Yeah, you simply have to understand what's going on. If I take the first functor, then if I have a particular morphism, let's say A1 to A2, yeah, I have a morphism from A1 to A2, and I have a map, I have a morphism from A to A1, then by using composition, I can define a map from A to A2. I can't do it the other way around unless I know some extra piece of information that I can always factor a map from A to A2 via a map from A1 to A2. If a priori I do not have any information, then this is the only way, this is the natural way to define it. On the other hand, if my object B is fixed, then a dual situation happens. Now, if I have a map from B1 to B2, then I need to have a map from B2 to B so that I can use composition to define a map from B1 to B. Okay. So, once you understand this, then you can also appreciate that, I mean, home C blank blank is actually a functor from C op cross C to sets. This is called a bifunctor. It's a bifunctor, which means it is a functor in two variables. Yeah, this is a bifunctor. I'm not going to make this concept precise, but bi means two. That's all you need to know. Okay, so any functor, now we have recently learnt about the notion of a natural transformation and natural isomorphism. So, any functor which is naturally isomorphic to a home functor is called a representable functor. Let me define that. So, definition: a functor f from C to sets is called representable if it is naturally isomorphic to a home functor. Yeah, I mean home functor of what form? Here I am asking for C to sets. Yeah, i.e. C A blank for some A in objects of C. Okay, something which is isomorphic to this. Now I will give you an example of such a representable functor. The simple example, all of you remember this forgetful functor from the category of groups to sets. Yeah, what does it do? It takes a group and it maps it to the underlying set. It forgets about the group structure, it only remembers the set. Now this functor is representable. Can you guess which object am I talking about? Which group in particular I am talking about? Integers. Home Z blank. What, like if you start with the group of integers and you are going to another group G, then what exactly is happening? 0 is mapping to identity of group G, 1 is mapping to some element, and as soon as 1 maps to something, then you already know where 2 goes, you know where n goes, you know where minus n goes, everything else is decided. And 1 has a free choice. Understood? 1 has a free choice, it can map to any element of group G, and then everything else is automatically determined. So basically, yeah, since U is naturally isomorphic to GR Z blank. When I say naturally isomorphic, now think about this, yeah, like i.e., I'm just remind you of simple thing, for any group G, UG, which is the underlying set, is precisely the set of group homomorphisms from Z to G. So even though, like, on the face of it, it's just a forgetful functor, but that forgetful functor is represented by a fixed object. You can do this, play this game with many things, and we are going to do that in, but the important thing about this representability is that whenever you find such an object, then you can also find one particular element which is called the universal element for this functor, which is important. So for example, in this case, what is that universal element? It's 1. 1 determines, like, wherever 1 goes, that's a different function. So 1 is a universal element, yeah, but I haven't defined what is universal element, and I need to do that first, yeah, then I can come back to this example and explain things to you properly. So let me go to the next slide, where we are going to talk about Yoneda lemma. You can say that this is perhaps the most important, most fundamental result in category theory. Yeah. If you have studied this course, then you must understand this particular lemma properly. Now, Yoneda lemma is named after Nobuo Yoneda, not MacLane, who was the founder, and there is a story associated with this. So Nobuo Yoneda was visiting France at that time in 1950s, and he was there for 1 year and he was about to leave. He had some discussions with MacLane. MacLane and Eilenberg had already laid down the foundations of category theory at that time. And when, Yoneda was only 24 at that time. And MacLane came to see him off. And they were at this North Paris, Gare du Paris North station. So North Paris station, railway station. He was about to leave. And they were at a cafe on the platform. And during that conversation, Yoneda mentioned something. Yeah, it was just a passing conversation in a cafe. And Yoneda mentioned something that was so profound that eventually MacLane decided to call it Yoneda lemma. He wrote about it in his book, Categories for Working Mathematician, and he gave the entire credit to this, even though Yoneda didn't even formalize it properly. He had this idea that I want to understand the collection of all functors. So basically the idea of representation theory has been around for quite some time. Yeah, representation theory is like the main philosophy for that is you start with a complicated object, you don't understand it very well, so you would like to study some effect of it in a category that you understand well. So for example, if I'm studying groups, yeah, then I could use G sets, group actions. I can study its action on different sets. One of those actions is going to be the action of G on itself. Yeah, so already the group multiplication is present in there, but the study of representations, like set representations, is more effective than the study of the group itself. Similarly, the study of rings, the study of rings is complicated because rings have got two operations. Compared to that, if you map it inside the map it to the category of abelian groups, if you take a functor to the category of abelian groups, then its representations are called modules. So in order to study a ring properly, you study its modules. Any complicated object, you represent it in a category that you understand well and you study the effect. However, sometimes you ask you start wondering, am I losing everything that I already knew about? Like, can I retain the information that I want to preserve? Now, if you have studied rings and modules, some algebra, then I'm going to give you one example. If I'm talking about a right module, okay, right module over a ring R, M, then I can rewrite it as this: home R, RR, MR. Right? Do you agree with this? Whenever I talk about a ring, I'm thinking of a ring with unit, identity, multiplicative identity. So this is always isomorphic. You can recover the elements, right? If it's a commutative ring, then you can also recover the module structure, but in general, you can recover the elements of that set. On this side, you are only going to recover, if it is a non-commutative ring, then I should be more precise and I should just say the group, abelian group, that you can recover. Because the same idea. It's if the ring happens to be the ring of integers, then every module is an abelian group and the elements of the abelian group can be recovered by just looking at homomorphisms from integers to that group. Simple idea.
So can we recover only the abelian group structure?
Only the abelian group structure. Right now I'm only talking about the set. Forget about the abelian group structure. Eventually when we'll do enriched categories, then we will see all these things in better detail.
Recovering the set, do you mean set up to like bijections?
Set up to bijection, yes. Set up to bijection, yes. So I can recover that, So what I'm saying that home RR blank is isomorphic to the forgetful functor. Again, I am saying the same thing. But I will also give you one other example that all of you have studied, even though you may not have studied rings and modules, but you have studied group theory. There is one representation theorem in group theory. It's called Cayley's theorem. What does Cayley's theorem say? Anybody? Every group G if is isomorphic to a subgroup of this group of symmetries of G. Very good. Very good. So now the group of symmetries is in some sense the origin. Symmetries are the origin of group theory. People wanted to study symmetries, that's why they started studying groups. So it's a representation. See, it's a representation. You are thinking of G as a G set. And then you are studying its representation. Now I want you to think about it a bit, okay? Now let G be a group. Thought of as a category. So how many objects are there in this category? One object. So G is actually isomorphic to home G star star, where star is the only object. Okay, so this is home G. and I'm thinking of G as a group. I will write it as both, yeah, if I need to. Now, what is a functor? A functor, G to sets, you have already seen this, yeah, is a G set, which means you are given, i.e., a set X together with a map G cross X to X. Yeah, this pair G comma X, it gets mapped to G dot X. That's the notation we are writing. Now I am asking you something more. Yeah. What is a natural transformation? Yeah, natural transformation. Maybe I am just calling this X, okay? X is a functor from G to sets. A natural transformation from X to Y, let's say alpha. What does it do? For each element in X, in category G, how many elements are there? And why are you talking about elements? Elements, yes, element is not the right choice of word here. Yeah, we are not doing set theory. We are doing category theory. So objects. How many objects are there? Only one. So you only need one map, basically. Yeah. So what map is that? It should be a function, like, yeah, is a function alpha from X to Y satisfying, I mean, it has to behave nicely with respect to the action also. Satisfying this, yeah, that G dot alpha X is equal to alpha of G dot X for all G in G and for all X in X. This is called an equivariant G map. Yeah, equivariant map between G sets. Equivariant means both actions are taken care of. Yeah, when I talk about G dot alpha X, you understand that it's about action in Y and G dot X is action in X. Yeah, okay. So this is equivariant map between G sets. And now I am going to ask you another question. So this is for any functor. Now I can choose one particular functor. What's that functor? Now I'll just pose it. What is home G blank singleton blank? For this particular object, what is this home? Symmetric group? No. I mean, I'll give you the answer. Answer is that it is G as a G set with left multiplication action. Think about this, yeah, why this is the case. Okay, so like you think about a ring as a module over itself, it's the same kind of thing. G as a G set with respect to left action. Okay, now I'm going to write something down. The set of natural transformations from home G star blank to home G star blank is in bijection with the set home G star star. So home G star blank is a representable functor, obviously. I mean, it's the home functor. So the set of natural transformations between these two home functors can be recovered as just the elements of the group G. So let me say it, yeah. The equivariant maps, the collection of equivariant maps between G as G sets with respect to left multiplication, that is in bijection with the collection of, that is in bijection with the group G itself. And since every element of group G is an isomorphism in the category G, correct? So everything works nicely here. And this is actually the statement of Cayley's theorem. Okay, I'm just going to write, this is Cayley. Whenever you are proving Cayley's theorem and stating it, this is perhaps a very convoluted and complicated way of stating something simple, but you can understand that what we are doing, we are taking G as a G set, and then we are asking amongst all the functions from G to G, which ones are G equivariant maps? Like amongst all the bijections from G to G, which is the symmetric group, yeah, amongst all the bijections from G to G, which ones are G equivariant maps? Well, they are precisely G many, size of G many. Like for every element, there is a G equivariant map, which is multiplication on the right. Yeah, if you try to go from RHS to RHS, it's multiplication by right, on the right. So this is Cayley's theorem.
So we have shown that these are natural transformations, but not natural isomorphisms.
That will also be true. Yeah, that's why I said like everything will work nicely because every element is like that. Every element is an isomorphism. Yeah. Now, what I am going to do is, Yoneda lemma is a generalization of that. Now look at this particular form. Yeah, I'm going to write a slightly different version of this. So this, it looks like this. Home G star blank, and to another functor, I'm going to say some functor f, which I don't know. Over here I can say x if x is the notation that we have used. This is in bijection with x applied on star. X is a functor from G to sets. So x applied on stars is going to give me a set. Yeah, so this set is in bijection with this set. That's what we are saying. And this is precisely the statement of Yoneda lemma. Let me state it formally and then we will prove it. And because I am writing a statement, I should make it precise. So I will say, let C be a locally small category. And, like A be an object, A an object of C, and F a functor from C to sets. Then there is a bijection between the set of natural transformations from the home functor Ca blank to the functor f and the set Fa. Moreover, yeah, the statement is not done here. This bijection is natural in both A and F. Okay, the second statement is hard to understand. I mean, that's where you will perhaps understand what is natural about natural transformation. Okay, and the first statement is relatively easy to prove. So let's go on and do that. So what do we need? We need two different maps. Yeah? And our only hint is that be natural. Do the obvious thing that you can do. So all of you are going to help me. Those who have seen this lemma, don't answer. Yeah? Those who haven't, they should answer. So what do we need? We need two different maps, some bijections. Yeah? So let capital phi, I am using this notation, be this set of natural be a map from set of natural transformations from Ca blank to F to Fa. Be defined by, now you tell me, what do we start with? A natural transformation. Yeah, alpha is a natural transformation from Ca blank to F. And where should I send it to? What is the data of a natural transformation? It has component morphisms. Yeah, component morphisms. One for each object of C. Now, do you know any object of C? A is the only object you know. So you have to use the eighth component of alpha. And then do you know any, I mean, see, alpha A is the only thing. Now alpha A has to take something. Alpha A goes from where to where? It goes from CAA to FA. And FA is a set and we just want to map it there. Now what can we do with this? Do you know anything from CAA? If you apply it on that, then you will go to FA. Do you know any morphism from A to A? Identity. That's the only thing you can do. That's the most natural thing you can do, and that's the map. Okay. And well, psi, let psi be defined from FA to the set of natural transformations. By the way, this set of natural transformations, is that a home set somewhere? I am writing NAT, but do you realize that that's also a home set? In which category? The category of functors, not, yeah, I mean this is same as inside this functor category, C sets, I am taking CA blank to F. Okay, so now you are given one element and you need to define a natural transformation. So you have got psi x. Psi x should be a natural transformation. So I need to define its component for any object B. So psi x sub B should be going from where to where? CAB to FB. Okay, now you have to tell me how to define this. If I start with a morphism, let's say F, where will I send it to? F is a morphism from A to B. I want to land inside FB. Image of what? Image of A. Image of A doesn't really make sense. Image is always associated with, I mean, you had to apply something, yeah? Image of what? If you know a morphism from A to B and you want to land inside FB and you know an element in FA,
FF of x.
FF of X, correct? That's the only thing you could do. So this is your, yeah, be defined by. Okay. Now we are not done yet. Yes, this psi x sub B, I mean psi x is a natural transformation that we have to prove. How do we show that? That psi x is a natural transformation? You have to start with, so I am just going to write it. Psi x is a natural transformation. What do you need to show? You have to start with two different objects and a morphism. So let's say I am given a morphism B to C, let's call it G. Then I will have two functors. I have the first functor CA blank. So I apply this. What is the vertical morphism, you tell me, from CAB to CAC? Composition, G composed with blank. Okay. By the way, G composed with blank, you can also find notation as CAG in literature. Yeah, because A is fixed and G is the thing that you are applying. Okay. Then you have another functor which is F, so you apply it on them, and this is just FG. Then you have something over here, CAB to FB. What is that? That's our psi x B component, and over here we have psi x, the C component, and we had to make sure this diagram commutes. Why does it commute? I'm going to use the diagram chasing option right now. Yeah, I start with some F. Where will F go under this? Okay. Where will this go under FG? FG of FF of X. You can't really do anything else. Okay, what about this? Where will F go under the vertical map? G composed with F. And where will this go? F of G composed with F at X. Are these two same? Because F is a functor, done. So psi x is indeed a natural transformation. We showed that. Good. So let's proceed. We have defined maps in both directions. What do we need to show? They are inverses of each other. It's a bijection, so we have to show it they are inverses. So which one should we do first? Let's do psi of phi. Yeah. So see, this proof is not hard. You just have to know where you are working. Yeah, psi of phi. What does that mean? Where should I apply it? Psi of phi. I should apply it on
Natural transformation.
a natural transformation. Very good. Very good. Alpha, I am starting with alpha. Where do I send it to? So phi of alpha is alpha sub a alpha sub a of 1 sub a, and psi only talks about one particular element. So that is the element. Alpha sub a 1 sub a is the element on which we are applying. So I'm just going to do this. So what should I put? I mean, psi of that is obviously going to be a natural transformation on some, let's say B again. Okay, so what is this component and what will it do? So it will start from CAB. Yeah, this is a morphism from CAB, and it will go to FB. Okay, what is the thing that is happening? I am mapping little f to what? FF of x. Yeah? FF of x. But what is x? Alpha A on identity of A. Okay, tell me what is it? Alpha is a natural transformation. Okay, so perhaps I should draw a diagram here in the corner to make sure you understand what's going on. So I just know two objects, A and B at the moment. Yeah, and I know one morphism. So I'm going to draw this morphism vertically, A to B. That's the morphism F, and alpha is a natural transformation. It goes from CAA, this is the alpha A component, to FA, and this is my component for B, CAB, alpha B to FB, and I have a vertical map here. So CAA to CAB, that is CAF, and this is what? FF. Oops. Okay, I will write it here, FF. I'll get rid of this part. Okay. So 1A is an element here. Now what you are asking for is 1A is taken across by alpha A and down by FF. Well, that is the same thing as going down first and then going across. So what is going down?
F of 1A.
F of? No, this is alpha sub B of F. Well, isn't that what you wanted? You started with some alpha and you wanted its bth component applied on F. Yeah, I mean alpha sub B of F composed with identity, and that's precisely what you wanted. You started with alpha, you got back alpha. Okay, verified. Now the second one. So the second one starts with this, like phi of psi. Okay, and what should I start with? Psi always applies on some element. Okay, and we had to make sure we get back what we started. We get back the same element. Maybe I'm, yes. So tell me, what does phi do? Phi says that whatever natural transformation you have, yeah, look at the top, you have to take its eighth component and apply on identity. So you have to take the eighth component of psi x and apply it on the identity. Okay, what is the eighth component of psi x? CAA, yes, and you have to send identity, so you will send it to f of identity applied at x. What is that? So f applied on identity is same as 1 sub fa applied on x. Well, x is indeed an element of fa, so one identity applied on x is just going to give you back x. Okay, so verification complete. You see, the proof is not hard once you understand how to define phi and psi. Yeah, and the definitions of phi and psi are natural. You could only do one thing because you had limited data and you could only do that thing. Yeah, that's the principle of category theory. If you can do the obvious thing and it works, then it works. Otherwise, it doesn't. Okay. So we have done the first part, that this particular bijection exists. Yeah, and I have also shown you the example here. Now you can understand what I was doing here. Yeah, like go back to Cayley's theorem. I took one representable functor, home functor, and what I am saying that the set of natural transformations from home G, like the representable to x, is in bijection with x evaluated at that, which is just the elements of set x. So if you understand this, like Cayley's theorem is a very, very special case of that. Another case that we saw earlier, that was this, a module being recovered. Now there is an application. I am not going to talk about naturality part yet. Yeah, let's enjoy the benefits of Yoneda lemma for some time, and that's, I'm not going to leave any space either. I will talk about that part later. So I am declaring that the proof is over except for naturality. Okay. So next thing is Yoneda embedding. So the way we have proved Yoneda lemma, what did we do? Like natural transformations which are home sets in the functor category and f of a. Now let us see how we can apply it to embed a category into a functor category. So again I am saying let C be a small, locally small category. Now why am I talking about locally small categories at all times? Because I am talking about category of sets. Yeah, if that were absent, then I don't need to. So let C be a locally small category. Then, okay, C, then the opposite category C op embeds inside C sets in a fully faithful manner. So you look at this, I mean, especially imagine that C is a small category and C sets is a very large category, right? Even if you consider C as a group, and C sets is the category of G sets, it's a large category, definitely. Now you are wondering what happens about like what happens to like the home sets. Are the home sets going to be too big? even between representable functors, is it going to be too big? The answer is no. There is a fully faithful embedding, which means the home sets are in bijection, so that every single object of C can be treated as an object of the functor category without losing its complexity. The complexity remains exactly the same. Now let's try to, and this, this embedding, we will denote it by Y for Yoneda, obviously. And what does it do? It takes C ops to C sets. It takes an object C to home C blank, and a morphism. Where will it take the morphism? If I have a morphism F, then it has to be in the.
It will take the compositions of the map.
Yes. So blank composed with F. Yeah, that's the map in the opposite direction, or it's also written as home C F blank. Yeah, that's the only natural direction. So I'm writing a morphism from C to D in category C, not in C op. You understand? I initially explained to you that home is a bifunctor from C op cross C. The first component is always contravariant, the second component is covariant. So therefore, when we are embedding this object, then it will be embedded as a representable functor, as a home functor in the first component. So in the first component, it has to be C op. Whereas the resulting functors are covariant. Good. So this is the Yoneda embedding. Let's prove that. What do we need to show? This is clearly a functor. Yeah, we just have to show it's fully faithful. How do we show fully faithful? So, I have to start with two different morphisms, two different objects of C sets, two different representable functors. So I'm taking this CA blank and CB blank. This is the home set in the functor category. But what is it in bijection with? If you remember Yoneda lemma, then the set of natural transformations from one representable to any other functor is just evaluate that any other functor at the original object. So which means I have to evaluate this second functor at this, which is nothing but CBA, which is nothing but C op AB. Right? It is in bijection with C op AB. Done? Yeah, there is nothing to prove after this. We needed that it is in bijection with the original home set in the original category. We got it. Yeah, this looks very simple, but in category theory, many arguments you just ask, why does this work? Yoneda. And it's an essential tool for doing literally anything. There is also something more which I'll just state it right now, that representable functors essentially generate the entire functor category. If C happens to be a small category, then representables generate the entire functor category, and they are also nice objects. If you have done some algebra, then you would probably know about projective and injective objects. So representables are projective objects and they generate the whole category. So under co-limits, to be more precise. So it's a very beautiful situation. Says that this large category, even though it's very large, yeah, it's still generated by a set, and that set is itself inside. It's an embedding. Yeah, I mean, you can see this small category living inside this large category and still controlling everything that happens there. Okay, so this is Yoneda embedding. Now obviously there are, in category theory, nothing is there without a dual, without a second version. So there will be a second version of this. So can you tell me what is the dual of Yoneda embedding? Sets to C. No. You just have to take dual in C. Sets of is a very bad category. Okay, we don't want to deal with that. I'm just going to write the dual version. I mean the other embedding, yeah, the dual Yoneda embedding. It doesn't start with C op, it starts with C and it goes to C op sets. Same thing, but no, you actually start working with this, then you will realize that the two things actually matter. Yeah, what is the functor here? C blank C. Okay. And maybe for your help, I can also write this, like there is a map this over here. This is a covariant functor. Yeah, C blank D, and this is C blank F, which is same as F composed with blank. So this is the dual Yoneda embedding. You could have done the same thing with, I mean, for proving that this is this dual Yoneda embedding lemma, you need dual Yoneda lemma as well. What does it state? Let me go back. It says that let C be a locally small category, A be an object of C, and F be a functor from C op to sets. Then there is a bijection between C natural transformations from C blank A to F and the set FA. Yeah, the same thing. So as an exercise, I would like you to try this particular thing. Okay. So now that we have done this nice part, we can return to representable functors. Have we left some space? Let me check. Yes. So we say that a functor is representable if it is naturally isomorphic to a home functor. But when we looked at this example, then we said that the element 1 in group Z is really important. It determines, it's a universal element. So what is that universal element? So let me define and then we'll proceed. So definition, suppose F from C to sets is representable, then a representation of F is a pair A comma X, where now we have to decide A comma X. So A is already, we said that CA blank is isomorphic to F. Yeah, that's what the definition is of a representable functor. So CA blank to F, but now we are saying that psi x is a natural isomorphism. Psi x will always exist. Where is x coming from? Tell me. X is an element. X is an element. Otherwise, we couldn't define psi x. Where is it coming from? Which set? Which set? Yes, correct. FA, correct. So, a representation of F is this pair, A comma X, where X is an element of FA, and psi X is the name of the morphism that we obtained there, natural transformation that we obtained there in Yoneda lemma. Okay. So, now you can you understand that, yeah, this X is called the element X is called a universal element for F. What is a universal element for the forgetful functor from groups to sets? That's 1. So, why is that 1? Well, continuing this example, So, I am treating 1, yeah, 1 is an element of UZ, right. So, what is psi of 1? From, GR Z blank to U. When I say psi 1, then I should talk about its component at a group. Yeah, the group, let's say it's G, so I put G here and then UG, and then you observe that you take any group homomorphism from Z to G and you send it to UF of like the underlying function applied at 1. Yeah, this indeed works. Yeah, I just tried to show you that 1 is a universal element for this functor. Okay. So, any question?
-1 is also a universal.
Is -1 also an element? Yes. Very good. So, how many such representations can there be?
Here I think 2
Only 2. But in general, there could be any number of representations. The point is that,
automorphisms of the representing object.
okay, let's not go into that, but in category theory, what is relevant is that you, however many representations there are, there is a unique isomorphism between them. Okay. So, we will do that. We will cover that, but let's look at some examples. So, another example, if you remember P star, have I written it correctly? Tell me, P star. P star is the dual power set functor. So, I should write op somewhere. So, I am going to write it here. Is representable. This is also an important fact. Yeah, the power set functor is representable. Now, you have to tell me by what. Yeah, here we are using the dual Yoneda lemma. So, it has to be isomorphic to something. What object is that?
The home set of
P star is isomorphic to sets blank
Two.
2 element set. Power set, what is a power set? Yeah, this characteristic functions, all the characteristic functions, right? So therefore, and now what is the universal element for this? The universal element and yeah, and a representation is, I mean, first of all, I have to talk about 2, which is 0, comma 1. Then I have to talk about f of a, which means I have to apply this functor on 2 first, which means I should choose something from the power set of 0, 1. And what is the accept state for characteristic function? We usually take it to be singleton 1. If you remember characteristic functions, yeah, every subset gets mapped to characteristic function, everything that is in that subset gets mapped to 1, and everything that is not in that subset gets mapped to 0. So singleton 1 is the accept state. So singleton 1 is the universal element from that power set. Okay, so that's how, I mean, you could have also chosen 0 if that's your definition. But as Suyash pointed out, there is only one up to isomorphism. Yeah, there is an isomorphism, and that isomorphism is also unique. Okay, so let me say the third one, third example. I'm talking about this pi n from HTPY star to the category of groups. Just think about pi 1. Here the fundamental group functor. That is also representable because the collection, I mean this, I am doing it over HTPY star, the set of homotopy equivalence classes, like homotopy classes of topological base topological spaces. You want homotopy classes of maps from what to the space X which preserve base point. What are the elements of the fundamental group at X naught? Since pi n of x naught contains as elements just talk about pi 1, homotopy equivalence classes of, correct, loops based at x naught. But what is a loop? Loop is a continuous map from S1 to X. In general, you have to take, yeah, HTPY star S1, Sn to X. I mean, maybe I should be more precise. I should say Sn1, this pair to x naught. Yeah. So, are you convinced that pi n's are also representable functors? What is the universal element here? The base point. Yeah. Or 1 in Z. Where is Z?
You apply pi n on Sn, 1.
Pi n I don't apply, like see, pi n of x comma x naught. Oh, pi n of Sn comma 1.
That is Z.
Uh-huh.
And there maybe 1 will be.
Right. Okay. So if you know that, correct. So pi n of Sn is always Z. Yeah. If you don't know that, then it's okay. But pi 1 of S1 is Z, that much you know, all of you. Yeah. With universal element 1 in Z isomorphic to pi n of Sn comma 1. Okay, good. So now let us finish that part where I am saying, and let me not prove it. The proof is by Yoneda. So suppose Ax and By are two representations of a representable functor f from C to sets, then there is a unique isomorphism f from A to B such that ff of x is equal to y. Okay, so it's an isomorphism. In general, we only get a morphism. Here we are claiming it's an isomorphism and it works. So how do you go about this? The proof idea is also very simple. So first of all, you have got C A blank and to F. You have this morphism. What is that? Psi of x. Yeah, this works. And over here now psi of x is an isomorphism. So I can also take its inverse. Here I am taking its inverse, psi of y inverse to CB blank. Right. So I have got two isomorphisms. And now it's a map, it's a natural transformation from CA blank to CB blank, which must correspond to a morphism from B to A, correct, by Yoneda lemma. Yoneda embedding, yeah, Yoneda embedding, it must correspond to a morphism from B to A, and that morphism must be an isomorphism. Okay, so this will give you a morphism which is an isomorphism between B and A. But still you haven't obtained this element. But you had to observe that this diagram commutes. Yeah, what is the diagram? Well, you also have, now that you obtained a morphism, you also have this this thing over here. From CB blank, CA blank to CB blank, what is the morphism there? From A to B, CA blank to CB blank, that is CF blank or F inverse, yeah. This F is from here to here, so but I think we obtained it from B to A. So this diagram will commute if and only if f of x is equal to y. Yeah, I mean for any morphism G, this diagram will commute if and only if it takes one universal element to another. So if you check that, then the proof is done. Yeah, here this f and f inverse is not exactly correct, but I mean if you want I can remove this minus sign from here, inverse sign, and maybe this is, let me call this G, so that you don't have to worry about what exactly I did inside.
I did not understand the last part.
Uh-huh.
C of f comma blank is from C a blank.
Yes, so there is a triangle here. Yeah, now the triangle has been formed. Now I am saying that for any morphism G, if I put that G in the top arrow, CG blank, then this diagram will commute if and only if G is equal to X. Fg of X is equal to Y. Otherwise it won't commute. And because we know this diagram commutes, that's how we obtained F. So therefore we have shown that it is unique, uniqueness of universal elements. So as Suyesh pointed out earlier, that for the forgetful functor example from groups to sets, yeah, what do we get? 1 is a universal element, and similarly minus 1 is also a universal element. But that's okay, because there is an automorphism of from Z to Z which takes 1 to minus 1. And that's the unique automorphism which takes 1 to minus 1. There can't exist anything else as an abelian group. Okay, so I'm going to extend it a bit, yeah, and I'm going to talk about this part which I missed. Yeah, this is the most important part. The bijection is natural in both A and F. So let me talk about this bijection. So naturality of bijection. Bijection in Yoneda lemma. I will tell you two different things. Yeah, the first one is the formal way of doing things. So naturality of this bijection means that I will take I have taken two different inputs, A and F, right? So I will say that there are two different functors, natural functors, and there is a natural isomorphism between them. That is naturality of bijection. But I will also try to explain to you what it means. Okay, so let me do the formal way first. First of all, I am starting with something from C cross C sets. And on this side I have got sets, and I am going to define two different functors. The first functor, let me use some different notation. Let me call this theta 1 and this is theta 2. So theta 1 will, now you have to tell me, you start with A and you start with F. What can you do with A and F to obtain a single set? FA, very good. Now, if I have a morphism in cross product of two categories is just component wise morphism. So you have a morphism from AF to BG. Well, it's a pair, let's say F comma alpha. Then here I am sending it to BG. But what will happen to F and alpha? Where will I send F alpha to in the category of sets? sorry, GB. I wrote BG but GB. You have got two different ways to move along, right? From FA you can go to FB, or from FA you can also go to GA. Very good. From GA you can go to GB, and from FB you can go to GB. So what is this map? This is F of F. This is G of F. This is alpha A, and this is G of A, alpha sub B. And this diagram commutes. So send it to the composition of either side. That's your first functor. So this is the definition of theta 1. Any question?
How does that map well define?
That map is well defined because this diagram commutes. This is the diagram for natural transformation. Yeah, that's why we can send it to this. And there is another functor. And for this another functor, you simply use something more formal. Sorry. See, we said, Yoneda lemma said that C can be embedded inside C offsets. I mean the dual Yoneda lemma. So embed it. Oh, sorry. C op can be embedded inside C sets. That's the actual Yoneda lemma. Let me show it to you. Yoneda embedding says that C op sits inside C sets. But that's also the same thing as saying C sits inside C sets op. I just take op on both sides. Yeah, I'm using that. So this sits inside C sets op cross C sets. The second component is just mapped as identity, and what can you do from these two things? Home. Very good. C sets and then blank blank. Sorry, I should write it over the functor, and I'm going to get down to sets. Yeah, this is one category op cross another cross the same category, and I can just take the home in this category and I will get down. So now I have got two different functors. This whole composition is theta 2. Okay. These two functors are naturally isomorphic. That is the naturality of bijection in Yoneda lemma. Now, yeah, I mean, just like you are laughing, like you don't get anything out of it. Yeah, what is it really trying to say? Yeah, these two things are naturally isomorphic. It's not going to help you. But what can help you is understanding what's really happening. So I will go back to the statement of Yoneda lemma. Yeah. So there is a natural set of natural transformations on one side and one particular set on another side. Now imagine, like, this is a bijection, so this bijection should be named something. We are naming it, right? Obviously we are naming it by phi. Let's say we say phi and we fix A. Fix F but we do not fix A. Then what will happen? So actually, I mean, I'm going to write it more precisely. This is a morphism which is indexed by F and A. Yeah, this is only valid for the given input. This is a bijection for this given pair. If I change the pair, I will get a different bijection. Now there are so many bijections. Are they compatible with the structure of the category? The answer is yes, and that is this naturality of bijections. So basically, if I have another object A prime and I take phi fa and phi fa prime, and there is a morphism from A to A prime, is it going to behave well with respect to this bijection? The answer is yes. So let me write one diagram. You can fill out the second one. Okay, let me say something. So we are starting with, so naturality for in A. In A of the bijection, like this is explicitly. So first thing first, like let me write down what we were doing. A to A prime, let's say there is a morphism. I am calling it H. Now we have a naturality here, natural transformations from CA blank to F. I am not going to change F in this discussion, and to FA, to elements of FA. What is the name of this? I am calling it, yes, phi FA, and that's all. No, I think I have to call it the other one, right? Correct. No, phi F is correct. Okay. Then over here I have natural, like this is A prime blank and then F. And over here I have got FA prime. And this particular bijection is labeled phi FA prime. Now here I have something very natural. FA to FA prime, F is a functor. So I have FH. What do I have here? There is something, okay, we said that home functor is contravariant in the first component. So what's the first component here? CA blank. So it should be contravariant. But CA blank itself in A, it is a contravariant functor. So two negatives make one positive. So ultimately, whatever this morphism is, I am just going to call it H star. I can call it nat CH blank F. Yeah, that's what is happening. Okay. So let me write what's happening. We have to start with one particular element. We have to start with some alpha, and that alpha has to go somewhere else. Where will alpha go? We know it must go to alpha sub A, 1 sub A. Whereas here, where should it go? To FA prime, FH of alpha sub A, 1 sub A. Yes, this is what we need. FH composed with alpha. FH of alpha A, this is always tricky, is phi F A prime of H star alpha. This is what we want. But H star alpha, whatever H star alpha is, yeah, that is what you get over here. S star alpha, alpha maps to S star alpha downwards. So that means you have to take H star alpha, the A primeth component of 1 sub A prime, which is alpha A prime of 1A composed with H, because that's what is happening inside these two contravariances, which is alpha A prime composed with CH blank applied on 1 sub A, and that's the proof, yeah, by naturality of alpha. So what we are saying is, just to put it in context of the axiom of choice, in axiom of choice we can make infinitely many choices at the same time. Yeah, it allows you to do that. Here what we are saying that we are choosing these bijections, but these bijections are not arbitrary choices of bijections. The bijections themselves behave nicely with respect to the composition, like the structure of the category and any category. Like here we talked about naturality in A, the other diagram is quite simple. Naturality in F, you fix A and you do vary F, you go from F to G. Yeah, so that's what naturality means, that you are making a coherent choice of several bijections at the same time. Usually, this part is something which is not focused on, yeah, but naturality is important. That's why it matters. Like everything is functorial, everything is natural. Any questions?
So this Yoneda lemma is based on taking functors to sets, but
Functors to sets is just this primitive version of this. We can, if we do enriched category theory, then we can take it to the enriching category. So for example, we can have an additive version of Yoneda lemma, yeah, like where everything, like home sets are abelian groups, and over there this home R, RR, MR, that will make sense as an abelian group. So there are versions, Yoneda lemma, like enriched Yoneda lemma, that's also possibility.
and the same proof works for
Same proof will work, yes, but the proof, this proof uses elements. You can avoid elements and still talk about things. Yeah, the enriched version will avoid elements. Yes.
How this that line from E star alpha,
H star alpha.
how the next line is,
This line,
yes, from that to the next.
from that to the next line. That's how it is defined, isn't it? H star alpha, what does it do? You have to work with this thing. I worked it out last night and then I came here. Yeah, so you have to work out this double contravariant functor
Using this for that diagram.
for this diagram. Yeah, CA blank. A is in the contravariant position of the contravariant position. So therefore you have to do that. It's not very hard. Okay, let's end it here.